Okay, I'm going to introduce something today called the coefficient of friction. And here's how we might think about it. So here I have a situation, a scenario where I have a table. On that table is a 10 kilogram mass, and it is attached to a 5 kilogram mass hanging over a pulley. Now let's just say that this table or this system right now is set up such that, such that this is just enough force that if I tap this little thing here, give it a little push with my finger. Yes, that's a finger. I push on it with a finger, and I break the static friction. It moves slowly at a constant velocity. What would that mean about my free body diagram? Well, let's look at that for a little bit. So I'm going to draw a free body diagram for that system right there, minus my finger. I'm not pushing it anymore. So in that case, here's my box. It is being acted on by gravity with a force of 100 newtons. The table is pushing up with a force of 100 newtons. So those are equal. I have a tension pulling to the right. Ready for this? Force of tension is 50 newtons, right? Because the force of gravity pulling down here is 50 newtons. And since I said it was moving at a constant velocity, once it starts moving, the force of friction is also 50 newtons. No accelerations. Everyone is happy. All right. So now let's say it's moving along. So this is my current condition, and I drop another 6 kilograms on it, and it stops. What has changed in our system? So what has changed in our system? A couple things. One, no longer is there a force of gravity of just 100 newtons acting down. There's the 100 newtons acting down on the box, plus then this other 6 kilograms is pushing down. So you have a second force of gravity, really the force of the other box, we'll say, not really force of gravity, I mean indirectly, of 60 newtons. So a total of 160 newtons down. Obviously, it's not now falling downward. So there's another, the normal force actually has to respond. The table responds with a force up equivalent to the total force down of 160 newtons. And wouldn't you know it, at this point, it stops. It no longer is moving at constant velocity. That means that the friction force, the coefficient, or not the coefficient, the sliding kinetic friction force has changed. It can be greater than 50 newtons. Now, of course, if it is currently stopped and just sitting there, this is still true. But the fact that it came to a stop means that at one moment, this force of friction, the force of sliding or static or of kinetic friction, was greater than 50 newtons. How did that get bigger in all this? Well, it turns out that if we zoom in here again, remember the friction is between these two surfaces trying to move, so the top surface trying to move across the bottom surface that's sitting there. And that friction force is actually not really just, we might often think it's dependent on the mass of this object, and it really is most of the time, but really what it's dependent on is how hard the table has to push up at that moment. It's dependent on the normal force right here. Now, when it's sitting horizontally, like we are in this case, that normal force is equal to the force down. In a little bit, we'll do a ramp problem to see that change. But this force right here is what determines this force right here. And the way that works is the force of friction is equal to some coefficient that is dependent on the surfaces that are interacting. So how rough the two surfaces are, how sticky the two surfaces are. And that coefficient, we use this funky letter, Greek letter mu, and you multiply that times the normal force. Now mu is, unless we're dealing with an adhesive, which is super duper ridiculously sticky, mu is generally going to be a number less than 1. Because it really is showing us the proportion of the normal force that is transferred into a force of friction. So if mu were 0.5, then that means that however big the normal force is, half of it then translates to a force of friction. So let's look at our current situation here and see what calculate our mu, or our coefficient of static friction. In our previous situation, when it was just slowly moving along, we had a normal force before this was true. We had a normal force of 100 newtons. Oh man, this is getting messy. Let's move over here. We had a normal force of 100 newtons. We had a force of friction of 50 newtons. And so if I plug that into that equation, 50 is equal to mu 100. Turns out it's exactly the scenario I just described. Divide both sides by 100, and I get mu is equal to 0.5. So that number, that 0.5, that is dependent, again, on these surfaces over here that are interacting with each other. So that would be a number that would be sort of a set value, that the coefficient of friction is 0.5 between those two substances.